In this video, we are going to talk about a common financial shortcut called a perpetuity. A perpetuity is an infinite set of cash flows. A regular or standard perpetuity is a constant stream of cash flows, like $5 every year, $10 every year, never changes. The way you would value this stream of cash flows is take the first cash flow divided by 1 plus interest twice, the second divided by 1 plus interest twice, the third divided by 1 plus interest 3 times, all the way out to forever. Now, as you go further out, the value of the cash flows keeps dropping because you're dividing by a larger and larger number. Turns out that eventually this sum converges to a fairly simple relationship. The present value is just the cash flow in any period, since they're all the same, divided by the interest rate. But a more intuitive way to show why this is the value of the cash flow is to ask ourselves how much it would cost us to generate this set of cash flows by putting our money in an investment or a bank account. So suppose that you would like to invest some money today to generate an infinite stream of cash flows of $5 every year forever. Let me propose that we take $100 and put it in the bank. We'll just call that the present value. After a year, $100 turns into $105. Let's take that as a cash flow and withdraw that $5 from the bank, leaving $100 in the bank for the next year. That, of course, will grow to $105 after I collect interest. Let me withdraw the same amount, leaving $100 in the bank. That turns into $105, withdraw $5. I can keep doing this forever. From my point of view, the cash flows are: give up the use of $100 today, I get to withdraw $5 every year forever. The $5 every year forever is exactly the pattern of fixed cash flows forever through time of a perpetuity. The cost today, or the value, is $100, and algebraically the relationship I'm seeing here is the present value earns me interest every year. I withdraw that, that becomes my cash flow. Solving for the present value, dividing both sides by interest, gives me the relationship present value of a perpetuity is C over R. Now, I'll show you a straightforward application, but this is simple enough that given any two out of these three variables, you should be able to find the third. A simple application might be you win a lottery, and the lottery gives you a choice of two prizes: $2.5 million every year forever, or $100,000 every year forever. To save space, I will use thousands of dollars, so I'll call this $2,500 and $100 each. What's the value of having $100 every year forever? Well, let's make a timeline. It's a perpetuity. The value of the perpetuity is the cash flow divided by interest rate. Calculating that out gives you $2,000. So the answer to this question boils down to whether you'd rather have $2,000 or $2,500 today. $2,500 is better, and that is independent of your preferences for the cash through time. Why? If you'd rather have $2,500 today, $2,500 is better than $2,000. If you'd rather have the cash across time, you can take the $2,500 today, put $2,000 in the bank. That would generate $100 every year in interest forever. Or you could take the full $2,500 and that would generate $125 every year that you can withdraw from the bank forever. So you could either deposit it, get $100 every year forever, and have an extra $500 left over today, or deposit it and get more in the future, $125. Either way, you like the $2,500 today better than the perpetuity value. The second shortcut we're going to talk about today is called the growth perpetuity. The only difference is that instead of having a fixed cash flow of, say, $3 next year, the cash flow grows by, say, 2% every year as we go into the future. Again, the way you would value that is take the first cash flow divided by interest once, second divided by interest twice, third divided by interest 3 times, all the way out to forever. Again, as long as the return is greater than the growth rate, this converges to a fairly simple relationship. Value today is cash flow next period. The timing is important, so I'm going to put that in here, C1, divided by return minus growth. Again, a more intuitive way to see that this is the right formula is to ask yourself how you could buy a set of cash flows that start next period at a certain amount and grow at a certain rate. So suppose that you want to buy by putting your money in an investment or the bank. $3 next year and have that grow at 2% per year. I'm going to propose we put $100 in the bank again. That will grow to $105. Now, if I took out the $5, it would stay constant. So what I'm going to do is I'm going to take out a little bit less. I'm going to take out $3, which leaves 102 in the bank. Now notice, that means my principal grows by 2%. If I invest that for another year, that's going to grow to, well, I'll get my calculator out for this. Let's see, 102 times 1.05, that's 107.10. Now I want to make a withdrawal that's 2% higher than last year, so that would be $3.06. And let's see, minus, that's going to leave 104.04 in the bank. And you want to check this, but that turns out to be 2% higher withdrawal and 2% higher principal in the bank. Leave that in the bank. It earns interest. And at the end of the year, oops, I have 109.24. Now, 2% more than 306. What is that? Okay. About 312. I'll withdraw that. Leaving me 612 in the bank. And again, check. This is 2% growth. This is 2% growth. Everything grows at 2%. And as long as I withdraw a constant fraction of the principal, 3% of it out every year, I leave 2% in to support growth. Okay. So my cash flow is the 5% I earn minus the 2% I leave in the bank to support growth. So again, my cash flows are, from my point of view, deposit $100, withdraw 306, and it grows constantly. And the relationship that sets this up is the present value earns interest at the rate of 5%, but I don't take that all out. My cash flow is the amount earned minus the 2% that I want to use to generate growth. Or in generic terms, collecting terms, it's the interest rate minus the growth rate. Solving this for present value, you just divide both sides. Cash flow next period will be important now, divided by return minus growth. So that is the relationship. Again, it's fairly simple. It's next period's cash flow, and that timing will be important. Divided by return minus growth, given any of the three, you should be able to figure out the fourth. We'll just do a simple example here. Suppose that you're a benefactor to the university and you'd like to endow a chair at the business school at the University of Iowa that will pay $150,000 next year and give a raise of 5% every year. If the endowment can earn a 10% return on investment, how much do you need to give them to generate this set of cash flows? Well, let me put it on a timeline. The cash flows are $150,000 next year, $150,000 plus 5%, $150 plus 5% again. That's the growth perpetuity. The present value of any growth perpetuity is next period's cash flow divided by return minus growth. And I believe if you calculate that out, you will get $3 million. Since everything's in thousands here, and again, it's a very simple formula. Given any three, you should be able to figure out the fourth item in this formula.